Hi everyone, good morning. So, welcome back to Renewable Energy Engineering, Solar, Wind and Biomass Energy Systems. Hope you had the essence of solar and biomass energy systems in the previous weeks. Now, we are ready to start wind energy systems. This is the first week of wind energy systems. In today's lecture, we will review the basics of wind energy systems, what is the source of wind energy, wind turbine terms, basic concepts and how to extract power from wind energy. The today's lecture is about introduction, wind speed versus height, history of wind turbine, wind energy regions in India, classification of wind turbine, main components of wind turbine, operating characteristics and mathematical expression governing wind power, design function requirements and then calculation of energy available in wind. So, before going into this lecture, we will review whatever we left with, right. In solar energy, in the third lecture, we had this wind energy basics, right. What is the source of wind energy? So, we will first review that, because in between you had biomass energy systems. So, we will review that and then slowly we will go to wind turbine terms, types and theories. For wind energy, the main factors are two main factors. One is absorption of solar energy on Earth's surface and in atmosphere, right. So, this is what we have discussed, how land is getting heated, how the lake side is getting heated. The second factor is nothing but the rotation of Earth about its own axis and its motion around the sun. So, due to these two main factors, so what we get is alternative heating and cooling cycles. Heating and cooling cycles. So, due to which the pressure difference is created. So, this pressure difference causes the air motion, and that is the way wind is created. So, if you see what is the ultimate source for wind energy is nothing but a solar energy. So, that is what we discussed probably in last lecture of solar energy utilization. So, then we should also know about its disadvantages and advantages. First, we will see about its advantage side, right. So, one is the potential as a source of power. Potential as a source of power is reasonably good, especially in India. So, the second one is no pollution, right, because the ultimate source is solar energy. So, we have these two advantages. But what is the disadvantage? The same disadvantages whatever we have discussed in the solar energy, right. One is dilute form of energy, the second one is availability, right. So, this varies day wise as well as season wise. only particular season you would get the required wind energy. So, this availability in terms of storage, and also the third one is we need large area, right, to capture the large area is required, right. And even if you go in depth, no constant mechanical or electrical output. So, this already we told the availability, it is an intermittent energy. So, whatever is applicable for solar is applicable for wind also, right. Aim is how to overcome disadvantages, how to maximize this as an advantage to draw power from wind energy. That is the main aim, to extract power from the wind energy. If you see the history, right, how or when this power extraction from wind energy was started. In ancient times, for sailing ships, this wind energy was used. So, almost a kind of little amount of mechanical power through windmills was used, and then the first horizontal axis horizontal axis 4 blade Dutch windmill. So, this was probably the one which started in 1200 ADs. Okay. So, this was mainly used for pumping the water. So, then Dutchies they introduced the same thing in USA in around 1700 AD, right. So, then with 4 blade system, the improved version of multi blade type, which generates about less than 1 kilowatt power, was developed in USA. So, with this improvement version. So, this also used for pumping the water as well as for generating electricity. Right. And after that what happened in 19th century, around 1920 to 1940, what happened is then other power plants of hydroelectric and thermal power plants, they took the front seat. So, this spending the research and development on wind energy extraction took the back seat. Then again around 1930, there is something called Smith-Putnam mission. Was developed. Right. So, this is major breakthrough. So, this was about 53.3 meter rotor dia and 28 RPM speed. It drew about 1250 kilowatt electrical power. Right. So, during this time there were many improvements in the design of the wind turbine. So, here 2 or 3 blade propeller systems were designed. So, there are a lot of improvement. There is one such kind of improvement is this one. And again what happened is in 1973, right. So, the major oil crisis. So, then the downhill of the wind energy picked up again. So, then after that new designs came up. Another major breakthrough is vertical axis windmills. Okay. And after this improvements, there were many few kilowatts to megawatt capacity and cost effective systems as well, right. So, economically viable systems were also designed. Okay. So, this is a brief history of wind energy. Anyway, we will see in depth. There are few other breakthroughs as well that we will see in depth. So, this is about worldwide and what happened in India, right. So, in India the major breakthrough was in 1980s, right. So, there are 5 states of India were identified, the coastal regions of 5 states of India were identified as the potential source of wind energy. So, which are Tamil Nadu, Maharashtra, Karnataka, Gujarat and Rajasthan, right. So, in these 5 states the total capacity of 3 megawatt windmills came for operation, and this 3 megawatt again splitted into around 0.5 megawatt in each coastal regions. So, this 0.5 megawatt also it is not a single machine. So, it is a kind of 55 kilowatt capacity machines altogether as a wind farm. And how it is operated, right. What practices being followed to draw the power from these windmills are to connect the machine to the grid and to feed power from the machines to grid whenever is available, right, because it is intermittent whenever power is available. Right. So, now then what is the scenario in India, right. Right now we already told for current installed capacity as well as the current generation capacity for solar energy from the arena. So, it is International Renewable Energy Agency. So, from this site you would get all the information, right. What is the current installed capacity of the wind energy and what is the generation capacity of the electrical power from wind energy system, all the data you would be able to get. And we will also see till 2015 what is the development in the subsequent slides. So, the one major breakthrough is of about 2.1 megawatt, right. So, this one was having cut-in cut-out speed, This terminologies you would see in this particular lecture. So, here we are discussing about the introduction of wind energy and whatever we discussed some 3 weeks before, right. So, what are all the sources of wind energy, etc. So, the cut-out speed is something about 25 meter per second and rotor dia of about 88 meter and the height of the hub, right. So, this terminologies you would get to know in this particular lecture. So, this is another big wind machine which was used to draw the electrical power, right, during the development of windmills for power generation. Okay. So, then we come to the windmills. What are all the types of windmills available? So, as we discussed, so one is horizontal axis windmills. The second one is vertical axis. Alright, sometimes this is called parallel axis as well. Why it is so? So, here it faces the direction of the wind. But unlike parallel axis windmills, vertical axis machines are independent of direction of the wind. Okay. So, in the horizontal again we may have different types, right. One is multi-blade system. So, by now you knew multi-blade system and propeller type. Right. So, the second is vertical. So, the famous designs are Savonius and Darius type. Okay. So, in the horizontal axis windmills, the rotor axis is horizontal, right. Based on that only it is called horizontal axis windmills, and also it is continuously adjusted in a horizontal plane. Also, in terms of wind direction, if you see, it is parallel to the wind direction, wind stream. Okay. So, that is what it is called as parallel axis machines as well. Right. Again we told there are two types, right. One is multi-blade system and propeller type. So, multi-blade systems are something like this. So, you have a inner rim and outer rim. So, in this your blades are attached. I just drew 4, but it is a multi-blade system, that is what it is. So, if you see, the width of the blade is increased from inner end to outer end, and inner end is fixed with one circular rim. The same way outer end also fixed with another circular rim. So, it is mostly containing 12 to 20 blades, right. Rotor dia is about 2 to 5 meter. Right. And also if you see the major components of this particular multi-blade horizontal axis wind machines. So, it is the rotor component which consists of blades, and then windmill head, tail van, and then transmission system. So, what is this transmission system? This again consists of power shaft, and then it may also have crankshaft, and then connecting rod, and then gearbox, and then pump rod. So, it is especially what we are seeing here is the rotor system which consists of this blade system, right. So, then it has to be kept in the rotor is connected with the windmill casing, right. We call it as a windmill head, and you will have one tail van at the rear side of the windmill, and then transmission system. So, this transmission system mostly kept in this particular casing. So, this has power shaft and then crankshaft and connecting rod and gearbox. So, this gearbox is mainly used to reduce the speed, right. So, there are two kind of motion, one is rotational motion and reciprocating motion. Reciprocating motion. So, this gearbox here, for example, if the multi-blade horizontal axis wind machine is used for pumping the water, if that is the application, then you might have this kind of transmission system. One is for power shaft and another is crankshaft and connecting rod. So, which converts the rotational moment and the reciprocating moment. So, that is connected to the pump rod, so which delivers this reciprocating motion for pumping the water. So, this gearbox, when you convert the rotational motion into reciprocating motion, so if you want to reduce the speed to 3 to 4 times, this gearbox mechanism can be used. Because we are not going to discuss anything in depth on the transmission system, because that is not our cup of tea to discuss in depth. So, here I am just telling like what are all it may contain, right. And other than this multi-blade system, so you will have propeller system as well in the horizontal axis wind machines. So, how does it look like? It looks like something of this kind. Right. So, this is propeller type. So, here rotor dia is higher than what we had seen in multi-blade system. So, rotor diameter is about 30 to 115 meter you can get. So, normally it may have 2 or 3 blades, not like multi-blade systems, right. So, the another important concepts we might need to be comfortable is the airfoil section, because these all blades have airfoil sections with the high thickness to chord ratio. So, why it is? It is to bring high lift. So, if you remember our introduction video, so we told that the drawing wind power mainly depends on two forces, one is lift force and another one is drag force, right. So, to elevate this lift force into higher value, so this all blades may have airfoil sections. So, airfoil section what you see in the normal flight, right. There are again many types, right. So, normally this is something called, we call it as symmetrical airfoil section. So, you will have lower surface symmetrical and upper surface no difference. So, there is a another type called camber airfoil section. So, in the camber airfoil section the upper face is curved . So, this is leading edge. So, this is trailing edge. So, this is lower surface, right. So, then what is this terminology? Chord ratio, right. The chord is nothing but, for example, so if you have this airfoil section with upper curved surface. So, this if you connect the trailing end with the leading end, so this is called chord length, and thickness is nothing but the distance between upper surface and the lower surface, right. So, this all are called thickness at particular point or particular length from the leading edge. So, if you connect the midpoint of all these thicknesses, right. So, if you draw a line, so that line is called camber line, right. So, the distance between the camber line and the chord length is called camber, right. So, that is what it is said that if you have a high thickness to chord ratio, then your lift force may be high, right. So, here the concept is like we have the theories based on which you will get this lift force, which is the upward force. So, one is based on Bernoulli's principle. The second one is flow turning principle. Okay. So, the Bernoulli's principle, which says that the energy per unit volume, right, energy per unit volume before and energy per unit volume after are same, right. What is this before after? So, this is particular section. So, this is a common diagram which is used in the Bernoulli principle. So, you will have the fluid which is entering with the V1 velocity, right, and pressure is P1. So, this is the section 2 where you would get a velocity V2 and P2, right. So, this is one is section 1, before is section 1, we can put it as 1 and after is 2. So, the energy conservation principle basically, right. So, if you see the area, right, so probably V1 is less than V2, right. The same way A1 is greater than A2 because the area is reduced. So, if this is happening, then based on this principle, so then your pressure at 2 should be less than pressure at 1. Okay. So, this is what is called Bernoulli principle. So, normally they equate the pressure energy and kinetic energy per unit volume. This is half rho V1 square plus rho g H1, which is nothing but a potential energy per unit volume, which is equivalent to pressure energy at point 2 plus kinetic energy at point 2 plus rho g H2, which is nothing but potential energy per unit volume at point 2, right. So, if both are same, then so whatever is happening with velocity, right. So, increase or decrease, that has to be compensated with the pressure increment or decrement, right. So, that is what basically happening here. So, how do I relate this to airfoil section? So, if you see the air is coming here with the free stream velocity. So, it has to see this stagnation point and take a curved shape of the airfoil section, and some of them go to lower surface as well, right. So, this is the way it happens. So, the upper surface, right, takes longer time, right, because it has to travel the larger surface. So, it may take high speed because the 1 and 2 has to be matched, right. The section 1 and section 2 has to be matched, matched in the sense energy per unit volume at 1 and 2 has to be matched. So, because of this larger surface area, it has to travel in faster speed, right. So, if the velocity is increased, right, so automatically pressure has to decrease. So, that is the way the upper surface of the airfoil, right. So, that has upper surface has higher velocity and lower pressure. So, the opposite is true for this is lower velocity, it is comparatively, right, it is not lower velocity in the sense not much lower, and higher pressure. So, this pressure difference, right. So, this pressure difference is exerting a force upward. So, that is called lift force. Okay. So, this is the basic principle involved in the rotation of the blade and how the lift forces create. There is another principle we told, it is nothing but flow turning principle. So, that is based on Newton's third law. Okay. So, this is something like, so whatever we have seen over there. So, this is inflowing impulse, right. So, if you see this figure, it has to take a downward, right. So, when it sees the stagnation point, so some of the air is travelling upward surface and part of that is also going downwards, right. So, this is inflowing impulse, and if you have airfoil section of this way, so if it is a outflowing impulse, so this is, so your resulting force is in this direction. Resulting forces acting in this direction. So, it is basically the lower surface redirects some of the air downwards. So, based on Newton's third law, so it has equal and opposite reaction. So, that opposite force is created as a upward force called lift. Okay. So, based on third law. So, if you are asking me, then why is it not the upper surface is also contributing to lift? Yes, of course. So, this also responsible for directing some of the air to downwards. So, totally it is just that opposite forces created upward, which is called lift. And there is another terminology also being used in the wind design, which is nothing but angle of attack. So, remember whatever we are doing here, we are learning the basic concepts involved in wind energy. So, we are not going to in depth here. So, we are learning terminologies, right. So, if it is a course exclusively for wind power extraction, then we might have discussed in depth about all these things. So, some of you, if you are working in mechanical or chemical engineering, so you might have learnt the course called fluid mechanics. So, in that you might have learnt in depth about all these things, but here the who are not part of these basic departments, who did not learn about fluid mechanics, I am just briefing about the terminologies. Okay. So, this is angle of attack. So, what is this? So, here you have a relative wind in particular direction, and you have your airfoil section of something like this. So, this card line is this one. So, this is relative wind direction. Okay. So, this angle is called angle of attack, right. So, the convention is that if alpha is higher, more air is being deflected downwards, right. So, more and more air is deflected downwards, then you will get equivalent and opposite lift force. So, that is the way also you get high lift. Okay. So, high lift force. So, that is something like the basic calculation, right. If we keep alpha is higher or positive, right, then you would also get high lift force. So, why we discussed all those things? Because of this particular terminology, right, when we are discussing about the propeller type horizontal windmills. So, there is something called thickness to chord ratio. So, if you get that particular ratio as high, then you would get high lift force. So, how the lift force is being created, that is what we discussed based on Bernoulli's principle and flow turning principle. Okay, so, coming back to here what we are discussing. So, we discussed about the horizontal axis windmill and we supposed to discuss about the vertical axis windmills. So, as we said earlier, there are again two types. One is Darius type, second one is Savonius type. So, what is Darius type? So, it is a kind of Professor Sohatmi book says it looks like a egg beater. Okay. So, to imagine, right, how it looks like. So, it also has airfoil section to create a high lift force, right, and also this shape is something called Troposkian shape, the blades. Okay. So, what is this particular shape? So, this is something like along the length the blades are curved. Okay. So, I am not good at drawing, but still we have this figure, but still we are discussing about introducing all the machines. So, here we will see also. So, here if you see, this is something called airfoil section. So, this is nothing but rotation. So, this blade is when it comes, so it is curved. Okay. So, this also curved this way. So, this is something called rotation. So, it rotates about. So, this particular shape is called Troposkian shape because the blades are curved along the length. And the next one is Savonius type, right. So, it is of this shape, right, S shape, but two halves of the hollow cylinders. So, this is hollow cylinder sliced half and all halves were fixed to a vertical axis. So, remember here in the vertical axis machine, the rotor axis is for both type. The rotor axis is fixed, right, and is vertical, and also it is perpendicular to both the surface of the earth as well as the wind stream, unlike horizontal axis machine. Okay. So, with the gap, so that is how it looks like as a kind of S shape. Okay. So, the torque is same way for both vertical as well as horizontal machine. The torque is produced by pressure difference. Produced by pressure difference. How it is created, then we have already seen in depth, right. So, this pressure difference is created between the half, right. So, this way and this way, which half facing the wind. Okay. So, this is what about the basic concepts and terminologies and what is the source of wind, so etc. We discussed, and now we will go and discuss in depth about whatever we discussed in brief. So, wind is basically caused by the solar energy irradiating the earth. So, the main reason is pressure difference between different regions. Wind carry enormous quantity of energy. So, this wind is used to provide mechanical power through wind turbines to turn electrical generators for electrical power. So, the regions in which strong wind prevails can utilize the wind energy for different purposes. So, there are two ways it can be created. The wind energy can be created in two ways. One is global convective circulation, another one is local convective circulation. This also we have seen in the solar energy utilization method. Global convective circulation is winds from the north to south in the northern hemisphere, from poles to equator. In local convective circulation, the differential heating between the land and water. So, the solar radiation during the day is converted into sensible energy of the land surface, right. So, this is happening in the land, right. So, when it receives the solar energy, so it receives amount of sensible energy, but what happens in the water? Partly absorbed in the layer below the water surface, one is absorption and another is whatever the absorbed energy partially consumed in evaporating some of the water. So, because of that, the temperature at the land side would be higher compared to water side, right. So, the warmer lighter air above the land rises and the cooler heavier air, this cooler and hotter, it is a comparative, right, between land and water, and heavier air above the water moves into replace it. Because of this pressure difference, so the wind is created because of air motion. At night, this cycle reverse, right, and hills and mountain also contribute wind energy because the air above the slopes heats up during the day and cools down at night more rapidly than air above the lowlands, right. So, these two are local convective circulation and global convective circulation from poles to equator. So, because of these two convective circulation, wind energy is being created. And the wind speed changes with height, right. Under normal condition, wind speed is greater at larger heights. This is again we can say wind speed is greater at larger heights, but whether it is same? No, because it is also depend on surface feature, turbulence of the air and degree of the cloud and roughness of the terrain. So, this is again related to surface features only, and the angle of the sun in the sky. So, this we have discussed, right, the motion of the earth about its axis and then sun. So, this all contributes this relation wind speed versus height, but in general wind speed is higher at larger heights. For example, surface features, right. So, when we talk about that, so there may be good sites, bad sites and can be improved. There are sites can be improved if we follow certain design procedure, right. That we will see probably in depth. So, for example, if you have a smooth hills like this, right. So, here if you construct your windmills, right. So, then your air also something like, because it is considered as a obstacle. So, you may probably getting waves here. So, here, so it will be something like smooth. Okay. So, this kind of sites we call it as a good sites, right, and there are sites which has sharp edges, right. So, such kind of surfaces you can expect turbulence at the top and bottom of the cliffs and sharp edges. Okay. So, there may be a wake formation here, right. So, it goes something like this. So, there here also you may get because of this sharp edges. So, a lot of energy being wasted in such kind of wake formation instead of converting into useful power. So, this we call it as a bad sites, which cannot be improved, probably naturally it is like that. And there are sites which can be improved, right. So, for example, you have a industry kind of thing, right. So, there also you have chimneys or something, right. So, when the air hits, right. So, here also you have kind of wake formation, right. For example, here you have a windmills, right. So, if you have a windmills here, so this is almost equivalent to the tower height, right. So, this is height of the tower. So, this is the diameter of the rotor, right. So, you would get such kind of obstacles when before air reaches to this rotors, right. So, here the general rule is that the distance between the obstacles and your windmill, right. So, that should be 10 times of height of this tower, right, plus in the sense greater than, right. So, the distance between the obstacles, any such kind of obstacles with the windmills, it should be greater than 10 h. H is nothing but a height of the windmill, and apart from that, to avoid this kind of obstacles here, you need to provide taller tower, right. Either you need to increase the h or increase the distance between the windmill and then the obstacles. So, this sites maybe it is due to obstacles, but if you carefully design your windmills, then it can be avoided. So, these are all comes as a surface features or roughness of the terrain and surface features etc. also come into play when we talk about wind speed versus height. Apart from that, you have obviously the wind turbine design, which takes part in this wind power extraction, but we are discussing here the physical factors probably, right, the sides, what are all good sides, what are all bad sides. So, the vertical variation of wind side is given by the power law, V upon V naught equal to H upon H naught power alpha. V is the wind speed at the required height H, right, and V naught is the wind speed at the original height H naught. Alpha is the surface roughness coefficient. So, this is given as 0.143 for flat coastal regions and less than 0.10 for tops of steep hills and around 0.25 for sheltered locations, and there are many locations for which the alpha is given already by fitting the data. So, that one can get in some standard book which are given in this particular lecture. So, almost all renewable energy except geothermal power ultimately comes from the sun. This we discussed many times, and here also some of them say tidal energy as well, but we do not include because we know this is tidal energy is based on rise and fall of the tides, but which is due to moon, but the thing is ultimately if you go in depth, that is also created due to sun power only. So, we do not take that as a exceptional things, but geothermal is obviously coming from the ground. So, we do not include them. In tidal energy also some of them say that it is not direct radiation of sun. So, it can be also included in the exceptional cases. And then earth receives around 1.74 into 10 to the power of 17 watts of power per hour. In that 1 to 2% is converted into wind energy, but if you compare with biomass, it is almost 50 to 100 times greater, 100 times greater if all plants of the earth, if all plants of the earth is converted into biomass. Okay, the comparison between the biomass and wind energy. So, winds are influenced by ground surface at altitudes up to 100 meters and slowed by surface roughness and obstacles. This we already have seen, right. So, surface roughness and obstacles slow down the air, but beyond the 100 meter you probably get lower turbulence and get good wind speed. And the force of the wind is converted into torque, right, which is acting on the rotor blades, which is again the power input to the turbine. The amount of energy which the wind transfers to the rotor, right. So, this is again function of density of the air, the rotor area and wind speed, right. So, if you talk about density, so we have already told that the kinetic energy is converted into electrical energy ultimately, right. So, the kinetic energy if you see half mv square. So, this is mass is related to density, mass upon volume, right. And also remember the density of the air, right, it also varies with the temperature, right. So, here it is told that the density decrease slightly with increasing humidity, also density decreases with increase in temperature. So, the convention is that heavier the air, more energy is received by the turbine. So, in that case you should not have higher humidity or higher temperature. So, that is nothing but the function of density of the air, rotor area and wind speed. And rotor area also, if diameter is doubled, so instead of d, if you get 2d, then it is twice 2 power 2 is your area. So, if area is increased, the amount of energy wind transfer also increases. A typical 600 kilowatt wind turbine has a rotor diameter of 43 to 44 meters. So, which comes around rotor area of 1500 square meters. And power generated by the windmill is based on the height, we already told, because up to 27 meter you would get very low power. Why? It is because of obstacles and surface roughness. So, when you go 27 to 33, it is about 300 kilowatt, 44 to 48 meter, it is about 750 kilowatt, and 70 to 80 meter if you go, you would get around 2500 kilowatt. It is all are approximate values. The rotor area determines how much energy a wind turbine is able to harvest from the wind. Then this I already told. If the turbine, which is twice as large in dia, will receive 4 times much energy because it is d square. The average annual wind speed of at least 12 miles per hour is a good location for the wind energy. So, this is what we call it as a good sites along with the surface features. This history we have already discussed, but still there are 7th BC century back. So, the major one is Panimon windmills, which are nothing but horizontal axis windmills. So, this was developed in Sistan, a region now in Iran and bordering Afghanistan, at least by the 9th century and possibly as early as 7th century. So, we have discussed recent one, and this is back history, much more back. So, and wind power for irrigation project in 17th century was developed by Babylonian Emperor Hammurabi, and first wind turbine used for the production of electricity was built in Scotland in July 1887 by Professor James Billett of Anderson's College, Glasgow, and world's first turbine of 1.25 megawatt, right, this is notable, was connected to the local electrical distribution system. So, this is in mountain known as Grand Pass Noben Castleton, Vermont, US, designed by Palmer Caslett Putnam and manufactured by the Morgan Smith company. So, this I probably discussed, right, 1.2 megawatt capacity Smith Putnam mission, and largest wind turbine of 8 megawatt capacity was developed known as Vestas V164 for offshore use. This is around in 2015. So, at the end of 2015, the total cumulative installed electricity generation capacity from wind is around 4,32,883 megawatt, which is 17% increment compared to the year 2014, and global wind power installations are equal to 63,330 megawatt. This is also at the end of 2015, but at the end of 2014 it was about 51,447 megawatt. And wind power installed capacity in terms of countries at the end of 2015, and China, it is 30,753 megawatt, 48.5% leading, and USA next one 8,598 megawatt, 13.5%. Then there are many in between, but we are interested in our country India, which is about 2,623 megawatt, which is about 4.1%. Recent statistics you can refer to ARENA, and wind energy conversion is nothing but The average speeds are higher in hilly and coastal area, this we discussed multiple times. Offshore wind is steadier and stronger than on land. Construction and maintenance costs are slightly higher if you want to go for offshore. The winds also tend to blow more consistently and with greater strength over the surface of the water due to less surface drag. This is important. And the factors affecting output power generation from the windmill are wind speed, cross section of the wind swept by the rotor, this we call it as a rotor area, and then overall conversion efficiency. It is not, there are theoretical limits for the efficiency that we are going to discuss in detail called Betz limit. So, out of this theoretical limit, again when it goes for practical installation, then you will have rotor, transmission system and generator or pump. Their conversion efficiency and their losses also included in the theoretical limit. No device, however well designed, can extract all of the wind energy, because what we said is we are converting kinetic energy into electrical power, right. So, what is that? Kinetic energy is nothing but a velocity, right, mass into velocity square of mv square. So, if you want to convert or extract all the wind energy, then you are supposed to stop the wind, right, at the rotor's face, but it will not happen. If you stop the air over there, the velocity becomes 0 and you will not have any more input air to for power production. So, because of that reason you cannot extract all of the wind energy. So, there is some theoretical limit, right, and rotor decelerates whole horizontal column of the intercepted air to about 1/3 of its free velocity. Not full velocity becomes 0, it is 1/3 of the velocity. So, that is called Betz limit, and conversion up to maximum of around 60% of the available energy in the wind into mechanical energy. That is what this limit called Betz limit, and a well designed blades will typically extract 70% of the theoretical maximum. Already theoretical maximum is 60%. In that 60%, a well designed blades, there is no losses from the blade side, then they can extract 70% of the theoretical maximum, but losses are incurred in the gearbox, transmission system, generator or pump, as I already said, could decrease overall wind turbine efficiency to 35% or loss. So, what is the generator or pump? So, if you want to use your wind power to pump the water, then the pump losses, or if you want to convert them into electrical power, then generator losses. That is why it is given generator or pump. So, this is mean wind speed map of India. So, if you see, this is the large capacity. So, as we discussed in brief introduction, so the GJ Gujarat as well as Rajasthan side, and here it is Maharashtra side, and here Karnataka side, and Tamil Nadu down south. So, this is having the maximum capacity for wind power production. So, this is taken from global wind atlas.info, and we have already discussed in depth about horizontal axis and vertical axis. This is what is the system look like. By now you know these are blades, rotor blades are propeller. So, this is nothing but hub which connects the shaft, right, the horizontal axis with the blade system, and then the next one is lower speed shaft, and this is probably not low speed shaft, it is high speed shaft. Okay. So, this is high speed shaft and this is gearbox, right. So, to multiple or to increase or decrease the speed, right, and this is the brake system. When cutout speed is reached and it automatically brakes the power generation, and this is the generator if you want to draw a electrical power from the wind power. So, this nacelle is nothing but the whole casing, right. So, this is the supporting structure or tower as far as horizontal axis windmills are concerned, right. So, here only I told, if you have, this is the two blade propeller type, or if you have multi blade system, the rotor only would get changed, right, and same time if you have a generator, you can draw electrical power, and if you want to use this windmill to pump the water, then you will have the gearbox. That is what I told, right, whether you want to use it as a reciprocating pump or centrifugal pump. If you want to use it for reciprocating pump, then you have to convert rotational motion into reciprocating motion using pump rod, and then you pump the water using windmill. Or if you want to collect the electrical power from the wind power, then generator is used. The next one is vertical axis windmills. So, this I have already discussed, right. The axis is vertical, it is fixed, right, and then it is perpendicular to the wind direction, and so these are the propeller types. So, these all are taken from web sources. Okay. So, this is a single blade horizontal axis wind turbine, this is double blade, this is 3 blade system, and this is offshore wind farms. Wind farms is nothing but I discussed, right, that 55 kilowatt capacity we combined to produce 0.5 megawatt capacity. So, this is the wind farm, and this is Darius vertical axis wind turbine, and this is Gorimal vertical axis wind turbine, this is twisted vertical axis wind turbine, and if you want to see Savius type, then it is of something like this is other side, right. So, this is the way air comes and it rotates, right. So, this is something called Savonius type. Okay. So, these are all available windmill models. In horizontal axis windmills, this horizontal axis machine has its blades rotating on an axis parallel to the ground. In addition, axis of blade of rotation is also parallel to the wind flow. These 2 points we have already seen. The rotor blades are connected to hub, you know what is hub by now, right. And horizontal axis machine shaft is mounted with bearings. The yaw control mechanism is used to adjust the nacelle around vertical axis so that it faces the wind, right. So, this is whole casing, this can be adjusted. So, based on the wind not direction. So, where you get maximum wind power. So, yaw control mechanism is used to adjust the nacelle around vertical axis so that it faces the wind directly, and whole assembly is mounted on the top of the tower. This is supporting system. So, the main thing is hub which connects the rotor blades, then after that you have a whole casing, in that all transmission system etc. is there, and yaw control mechanism is the one which adjusts the nacelle around the vertical axis. The electromagnetic brakes are used for automatic applications of brakes if wind speed is larger than the designed speed, that is what we call it as a cutout speed. And commonly found horizontal axis windmills are aeroturbine mills, which has the efficiency of 35%, and farm windmills of having 15% efficiency, because the horizontal axis windmills are popular one in terms of efficiency, and yeah, we will see the advantages and disadvantages. And horizontal axis wind turbine type can be further classified based on their rotor diameter, right, as large rotor diameter, which is about 150 meter, which draws 3 megawatt capacity power, and medium rotor diameter, which is 50 to 100 meter, which draws power of about 500 kilowatt to 1.5 megawatt, and domestic ones which are less than 50 meter and which draws power about 10 to 250 kilowatt. And then we have mini micro scales as well, which are less than 25 meter rotor diameter, which draws less than 10 kilowatt power. In vertical axis machine, they are having their blades rotating on an axis perpendicular to the ground, and vertical axis machine need not to be oriented with respect to wind direction. This we have already seen. and because the shaft is vertical, the transmission and generator can be mounted at the ground level, allowing easier servicing. So, for horizontal mission you supposed to keep it in the higher height, right, with the supporting structure, but one advantage is because the shaft is vertical, you can have transmission system as well as generator in the ground level itself, and lighter weight and lower cost tower, right. But although vertical axis wind turbines have these advantage of the maintenance or servicing or in terms of weight and cost, their designs are not as efficient at collecting energy from the wind as are the horizontal mission designs, because they are kept in the direction of the wind only. So, efficiency wise horizontal axis wind turbines are good, but in terms of maintenance and flexibility one can go for vertical axis windmills. There is one more type windmill called cyclogyro windmill with high efficiency of about 60%, but however, it is not very stable and it is very sensitive to the wind direction. It is also very complex to build. And this is again few points about the various components of the horizontal axis wind machine. So, the rotor is the portion of the wind turbine that collects energy from the wind, is called rotor, and the rotor usually consists of two or more wooden fiberglass or metal blades which rotate about its axis, horizontal or vertical, based on the windmill at a rate determined by the wind speed and the shape of the blades, right. This is important, wind speed and the shape of the blades. That is why we have many designs, because wind speed you cannot control, it is a nature's thing, but how to draw maximum power you can do it by using shape of the blades. The blades are attached to the hub, this is hub which is again attached to the main shaft. So, this is main shaft. The transmission line, the number of revolutions per minute of a wind turbine rotor can range between 40 to 400 RPM depending on the model and the wind speed, but generator typically require RPMs of around 1200 to 800. So, which can help us, that is nothing but a gearbox transmission to increase the rotation of generator to the speeds necessary for efficient energy protection. Some DC type wind turbines also there which do not use transmission boxes. Instead, they have a direct link between the rotor and generator known as direct drive systems. Without transmission, wind turbine complexity and maintenance requirements are reduced. In that way, DC type wind turbines are good, but the thing is what power we require is AC probably, then there should be a converter as well. So, the generator is what converts the turning motion of a wind turbine blades into electricity. So, inside this component of generator there would be a coils of wire rotated in a magnetic field to produce electricity. This you might have had all these things in your school level physics. We are not going in detail anything about electrical energy protection part of this wind energy system. So, the different generator designs produce either alternating current or direct current, and they are available in large range of output power rating. The generator rating or size is depend on the length of the wind turbine blade, because more energy is captured by longer blades. If more energy is captured, so you need that rated generator for electrical output. It is important to select the right type of the generator to match the intended use. It is based on the designer, right, who designs to convert the wind power into electrical power. So, tower is nothing but on which wind turbine is mounted, and is not just a support structure, it also rises the wind turbine so that its blades safely clear the ground, and so it can reach the stronger winds at the higher elevation. So, that is not only support structure, it also helps in getting more wind power. Maximum tower height is optional in most cases except where zoning restrictions apply. This also we have seen during the obstacles section of the zones. And larger wind turbines are usually mounted on towers ranging from 40 to 70 meters tall. So, this is normal height. So, this also we have seen height versus the drawing power. So, this mathematical expression governing the wind power we will continue in our next class. References used for this particular lecture is these three references: Suhatme and Nayak, Solar Energy Principles, Thermal Collection and Storage; and S. Matthew, Wind Energy Fundamentals, Resource Analysis and Economics, and Manuel et al., Wind Energy Explained, Theory, Design and Applications. Thank you.